Welcome back. This is the second part of our lecture 15 on Introduction to Combinatorics. So in this second part, we are going to cover a number of problems, and we'll see how to solve them using the concepts we introduced in the part 1 of this lecture. And we will also look into a concept called combinatorial equivalence. And explain what that is all about. Okay, so let's first solve a couple of problems. So before we do that, this is a quick reminder of the terminology that we introduced last time, and it does that by giving examples of all of the different structures we learned about. So, for example, when you are dealing a 5-card poker hand, in this case, the order doesn't matter, and every card is unique, which means that there is no repetition, and the structure that captures that is a set. Then, when we're dealing a 2-card blackjack from one deck, the order does matter, since one card is up and the one is down, and also every card is unique, so there is again no repetition. So these are permutations. We're ordering an ice cream cone with 2 scoops. The order matters. We have bottom scoop and top scoop. And in this case, repeats are allowed. For example, we can have chocolate both on top and bottom. So this is an order list. When we are filling a jar with various types of candy, that's an unordered list or bag. Seeing the order does not matter, and repeats are allowed. Okay. This is a refresher of our rule of products. So you remember in part 1, we drew this tree that represents drawing 3 digits chosen from 1, 3, 5, 7, 9 with no repeats. And then the question was how many leaves are in this tree, and we solved it using the rule of product. Note that this can be also solved using permutations. So we are choosing 3 digits. There is no repetition from the set of 5 digits, and so the solution is B5, 3. So often there are several different ways of solving the same problem. Okay, so let's do this practice problem. Consider a best of 5 match in which the first player to win 3 sets wins the match. We have to draw a tree to represent such a match between players A and B. Okay, so first we're going to draw first match. They can be won either by A or B. So let's say this is A wins first match, this is B wins first match. Then from here, they both branch into second match. So here we have A wins second match, here we have B wins second match, and the same goes for this. Here we have A wins second match, and here we have B wins second match. Okay, now the third match, we branch more. So we have A wins the third match, we have B wins the third match. Here we have A wins the third match, and B wins the third match. Here we have A wins the third match, and B wins the third match, and so on. Again, A, B. One difference with the tree in the previous example is that some of the branches are going to terminate now. For example, when we are at this point, A won 3 matches, and so we will not keep expanding this branch. The same goes for the last one when B won 3 matches. That means that they won best of 5, and at that point we stop. And then these guys are still going to be expanded. So that's how you would draw this tree. And then once you draw the whole thing, you can kind of count various types of outcomes. So now that we sketched out this tree, we can use it to answer different questions about this best of 5 match. For example, how many ways are there for the match to end after just 3 sets? There are only 2. Either A wins all 3 sets or B wins all 3 sets. How many ways are there for player A to win in exactly 4 sets? Well, let's think about this. So it can be, so player A has to win 3 out of these 4 sets. So it can be B, A, 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 B, A, A, or A, A, B, A. So there are 3 different ways for player A to win in exactly 4 sets. Finally, explain why the answer to the previous question is the same as the answer to the question how many ordered lists of length 3 from AB have exactly 2 A's. So these are the same because for player A to win in exactly 4 sets, we know that the 4th set has to be A's win. And so we're looking then at ordered lists of length 3 that have exactly 2 A's. So they have 2 wins. So that's why these two are identical. Now we'll introduce the concept of combinatorial equivalence, which tells us about one-to-one correspondence between finite sets and recognizing the 2 sets are the same, meaning that they have the same number of elements. So here's a simple example that illustrates combinatorial equivalence. So the question is how many multiples of 3 there are between 1 and 100 inclusive. So we can try to enumerate them. So we know that they have to be divisible by 3, so 3 has to be one of the factors. So we have 3 times 1 is 3, 3 times 2 is 6, all the way to 3 times 33 is 99, and 3 times 34 is greater than 100, so we exclude those. So how many there are? What is the easiest way to count this? Well, we can invert this, and instead of counting how many multiples there are, we can count these multipliers here, because those go from 1 to 33, and so it's easy to count them. So the question is, how big is this set? Well, it's trivial to see that there is 33 elements in this set, and that's the same number as the number of elements in this set. So these 2 sets are combinatorial equivalent. They have the same number of elements. But arguably, the first one is a little bit easier to count. And so by counting the elements in the first one, we can determine the number of elements in the second one, which is what we use combinatorial equivalence for. Here is another example. How many ways are there to distribute 3 coins, penny, nickel, and dime to 10 children? So let's number the children from 0 to 9, and then ask ourselves how many numbers are there in the set of numbers from 0 to 999. So there are 1,000 such numbers. So this is clearly easy to count, and as it turns out, these 2 are equivalent. Why? So we can think of the digit in the hundreds place to denote the child to which we are giving to a penny, the tens place to the child to which we are giving to the nickel, and the first ones place denotes the child to which we are giving to dime. So 369 denotes giving 1 penny to child 3, 5 cents to child 6, and 10 cents to child 9. 5.20, 1 penny to child 5, 5 cents to child 2, and dime to child 0. Now, child number 0 is a little bit tricky because clearly because we don't really have numbers that start with 0. And so all numbers that have 1 digit or 2 digits, we can think of them as starting with 0. So number 0 is basically 0, 0, 0, and it means that we are giving all coins to child 0. Number 1 is 0, 0, 1. So we are giving the first 2 coins to child 0 and the last one to child 1, and so on. And so this again illustrates the equivalence between the first problem and the second one, where the second one is much easier to count. Okay, example 2, this is a well-known noun. The number of binary sequences of length 10 is equal to the number of elements in the power set of this set that has 10 elements. And here is how we will set up the equivalence. So each, in this sequence, the first element in the sequence represents number 1 from this set, the second element number 2, the third element number 3, and so on. And whenever there is 1, this element is present in this element of the power set, and when there's 0, it's not present. So this represents 1, 6 because it has 1 at the first and 6th position. This represents 3, 4, 7, 8 because it has 1s in position 3, 4, and 7, 8. Empty set is represented with all zeros. What would this one be? So it has 1 at the 2nd position. It has 1 at the 4th position. 1, 2, 3, 4 at the 6th position. And it has 1 at the 9th and 10th position. So this sequence will represent the set 2, 4, 6, 9, 10. Okay. So then it's easy to calculate the number of sets in the power set. So it's going to be equal to 2 to the power of the number of elements in the set, to the power of 10. Okay, so then as example 3, the number of sets of size 2 from the number of subsets, I should say, of size 2 from the set that contains 9 elements is equal to the number of subsets of 7 from the same set. And here is how we set up the equivalence. So the subset 1, 2 is equivalent to 3, 4, 5, 6, 7, 8, 9. So we exclude 1, 2. 4, 8 is then going to be equivalent to 1, 2, 3, 5, 6, 7, 9. And so on. So if we let set A be equal to this set of digits, and B be subset of A, such that the number of elements is B is 2, then C is equal to A minus B, and the number of subset B is the same as the number of subset C. So this is how we set up the combinatorial equivalence in this case. So this is the last example in this series that we'll take a look at. And this one is a little bit harder. So we are trying to count how many positive integer solutions there are for x, y, and z, such that x plus y plus z is equal to 21. And we are going to calculate that by showing that it's combinatorial equivalent to answering the question of how many two-element subsets of the set that goes from 1 to 20 there are. So this one, the second one, we know how to calculate. That's easy. And if we can show correspondence, we can calculate the solution to the first one by calculating the solution to the second one. So there are a couple of things to notice here to set up this correspondence. So first, know that once x and y are chosen, z is set. So z is going to be equal to 21 minus x minus y. So we cannot choose z, and so we can disregard it. Also, since y is greater than 0, x and x plus y do not have the same value. So x and x plus y will definitely be different. And since z is greater than 0, we know that x plus y has to be less than or equal to 20. So here are a couple of examples showing how we set up the correspondence. So if we have the solution 1 plus 2 plus 18 is equal to 21, this is going to, we can disregard z, and this is going to correspond to this two-element subset containing 1 and 3, where 1, the smaller number is x, and the larger number is x plus y. Same here. Smaller number is x, larger number is x plus y. So if we apply this strategy, 10 plus 1 plus 10 is equal to 1 is going to correspond to subset 10, 11, and 4, 9 is corresponding to the solution where x is 4 plus y is 5, because x plus y has to be equal to 9. And then we have to compute z. Z is equal to 12, and that's equal to 21. So that sets up the correspondence, and now we can easily calculate the number of these solutions.